So, we will be taking up several other numerical problems on quality and reliability. So, this session we will be referring to other typical numerical problems on quality and reliability. Now, in the previous lecture session, we have explained with respect to one particular numerical problem how to construct the OC curve for the P control chart. Okay. Now, for constructing OC curve for the C control chart, we follow the same procedure, but need to be careful about certain notations. Okay. As you are already aware that the basis of constructing a C control chart is Poisson distribution. Okay. And C control chart is used to control the number of the non-conformities or the defects on a particular product. Now, operating characteristics curves when we refer to, that means whenever we refer to the operating characteristics curves for a specific control chart, first what you have to consider, that means for this particular case, that means for the C control chart, the number of non-conformities, that means what could be the possible the values of the number of non-conformities. And the C control chart, we assume that the sample size remains constant. So, if the process average number of non-conformities is C, is it okay? So, that's the parameter. The probability of a type 2 error is given by this. That means this is the beta function probability that x. What is x? X is basically a random variable. That means the number of non-conformities. Now, this is this value is less than upper control limit for the C control chart for the given value of C. Is it okay? And this is the probability minus probability that x is less than LC. Is it okay? That means the area between the upper control limit and the lower control limit for the C control chart given a particular value of C, where x represents the number of non-conformities, that's already I have mentioned, for a process average of C. Incidentally, x is distributed according to a Poisson random variable. Is it okay? That is the basic assumptions we make. With mean C, since the value of x must be an integer and UCLC and LCLC need not be integers. It could be 17.3. So, obviously, it is an integer. And similarly, LC lower control limit for the C control chart could be 1.73 or 2.53. Is it okay? So, in all likelihood, they may not be the integers. So, what to do? That means you need to make some corrections. So, for making corrections in the formula, what you do, that we say that the beta is probability that x is less than equals to, okay, UCL, okay, absolute value of UCL given a value of C minus probability that x is less than equals to LCL. That means some absolute value of LCL, okay, given the value of C, where UCL absolute represents the largest integer less than or equal to the UCL. So, this rule you have to follow. Largest integer less than or equal to the UCL. That means suppose it is 8.56, it has to be 8. Is it okay? And similarly, this LCL represents the smallest integer greater than or equal to the LCL. Suppose the LCL is say 0.73, that means it must be made 1. Is it okay? So, these corrections for integers you must make in the formulation, and then we take off this particular example. Is it okay? samples of fabric from a textile mill, each 100 square meter are selected, and the number, that means the sample size is constant. It is for any sample, it is 100 square meter, and the number of occurrences of foreign matters, that's if you have the occurrences of foreign matters, that means is considered to be certain defects. So this the occurrences are recorded, which deals with the number of occurrences of foreign matter in fabric samples. The revised central line of the C chart is 7.208, and the revised control limits are this 15.262. Is it okay? So, and the lower control limit is 0. So, the lower control limit is 0, the central line is 7.208, and the upper control limit is 15.262. Is it okay? This is we are referring to the final control chart. Construct an OC curve for this chart. So, what you try to do, that means we assume that a type 2 error is committed when an observation falls strictly within the control limits. Is it okay? Even if there is a shift in the process parameter value. Now, we have to construct a table, and the table gives the probabilities of various values of C. That means the probabilities of for various values of C. Probabilities of what? That means the probability of making type 2 error given a set of upper control limit and the lower control limit for the control chart. Okay. So, using the previous equation, we get here beta is probability that x is equals to less than equals to 15.262 LCL given a value of C, minus probability that x is less than equals to 0, that means lower control limit is 0, that is given a value of C. So, these corrections we make in for integers. So, x is less than equals to 15, is it okay, and x is less than equals to 0, right. So, after making these corrections, then for a given value of C, say 0.5, 1, 3 and so on, we calculate the corresponding values of this probability as well as probability of this one. Is it okay? So, we refer to the Poisson distribution table, more specifically cumulative Poisson distribution table, and this probability you compute, this probability also you compute, and you subtract this from this. So, you get 0.393. So, the same procedure you follow for all the possible values of C. So, what is the basic assumption? The basic assumption is that these C values are the feasible. That means there is a possibility that that the number of the non-conformities may assume all these values. Is it okay? So, you have to be careful. It just cannot be any value. That means you must have some experience related to that particular the product quality, and then you say that this might occur. So, suppose the C value could be as high as 20. So, what is the probability of the detection? Probability of detection is 1 minus 0.157. Basically, this is the beta. Beta means probability of non-detection of the shift. So, as you might have noticed that as the value of C increases, the probability of non-detection decreases, and that means the probability of detection increases. Okay. So, that is the typical so the nature or the property of is a general purpose control chart. So, when you plot all these values, okay, so you get a curve of beta versus C, possible values of C. So, you have a typical the OC curve, it looks like this, okay, for the C control chart, right. So, this will be a good exercise for you, and so these numerical problems, that means whenever you use a control chart, so you must be in a position to construct the OC curve, and we look at the OC curve, and looking at the OC curve you can well interpret the performance of your control chart. Is it okay? So now the next examples we are talking about, that is related to the reliability. Is it okay? So whenever we discuss reliability, we refer to say component reliability, we refer to the system's reliability, and whenever we refer to the system reliability, now the system is a structure needs to be explained with respect to its configuration. So there are the two pure configurations we have already referred to. One configuration is a series configuration, and the second one is as an alternative to series, it could be a parallel configuration. Now here in this particular example, what we are saying that a complex system has 600 components in series. Now whenever we define the complexity of a system, now the complexity of a system can be explained from several perspectives of so the quality and reliability. Now in this case the complexity is explained or defined with respect to the number of components you use. Is it okay? So there are 600 components, so obviously in all likelihood it may be referred to as a complex system. The reliability of each individual component is 0.998. Okay, I am not assuming it to be 1, it just cannot be 1. Is it okay? It could be very almost nearing 1, but it just cannot be 1. So 0.998. Determine the reliability of the system, and if the number of components in series is reduced to 500, find the reliability of the resulting system. So this is the system reliability 0.998 to the power 600, that is 0.3008. So the system reliability is only 30.08%. If the number of components in the series systems is reduced to 500, the reliability of this system is this. Is it okay? 36.75% system. So this is just a simple example, right? That means here what you will find that even if the individual component reliability is very high, if you deal with a series systems, in all likelihood that the overall system's reliability will be very, very poor. So how to improve the system's reliability? The first approach is, can you reduce the number of components? Okay, so this is one typical example I got through. Next we go to the next examples on reliability. The transmission unit of a mechanical system has 15 components in series. This is very, very typical. Each individual component has an exponential time to failure distribution with a constant failure rate of this. Is it all right? That means 0.04 per 5000 hours. Now the obvious question is, how do you get this value? Through experimentation, right? So 0.04, that is the failure rate, or if you refer to the past data, right, you have this estimate 0.04 per 5000 hours. Is it okay? So per 1000 hours, what will be the failure rate? That means 0.04 divided by 5. Is it okay? Find the reliability of each individual component after 300 hours of operation. That means, as you know, that whenever we define reliability, reliability is defined with respect to a specific time period, okay, the survival time. Find the reliability of the transmission unit for 3000 hours of operation. Okay, this is for the individual component and this is for the entire system. Determine the mean time to failure, MTTF. We have already discussed how do you compute or how do you get the expressions for MTTF under different distributional assumptions for the time to failure. If the desired system reliability for the transmission on unit is 0.98 after 3000 hours of operation, determine the mean time to failure of the individual components. That means these are the 4 questions we have set. Now the failure rate of individual component I have already mentioned, that is lambda, that is per hour basis. If you compute, you will find 0.04 divided by 5000. that means 8 into 10 to the power minus 6 hours. Is it okay? So that is the value of lambda, and we are assuming that the lambda is constant. That means all the components as well as the systems are in useful life phase. So reliability of each component after 3000 of operations, that means R, that is the reliability, e to the power minus the lambda t. So the lambda value already have computed, that is 8 into 10 to the power minus 6, and the value of t is 3000. Is it okay? Because we are computing the value of reliability for 3000 hours, okay, the time period. So that means this is 0.9763. The reliability of the transmission unit after 3000 hours of component is basically, R5. That means it is exponential 15 times. There are 15 components. Okay, that means it is sigma lambda I into t. So what is lambda I? That means each one is having this lambda. Okay, so how many say the components you have? The 15. So each one is identical to the other one. That's why it is 15 into 8 into 10 to the power minus 6. That means the time to failure for the system is also the exponential. Is it okay? So that is the assumption. So 3000 hours. So it has come down to, this value of reliability has come down to 0.6375. Is it okay? So this is RS. Is it okay? So systems reliability, that notation we have used, 0.6376. So it is considered to be very, very poor. The mean time to failure, obviously MTTF is 1 upon n sigma lambda I. So sigma from I equals to 1 to 15, right? So 15 into 8 into 10 to the power minus 6, that means 8333.34 hours. That is the mean time to repair, mean time to failure. Now let for the the next questions, what you assume that the lambda is equal to failure rate of the transmission unit. That means transmission unit is considered to be the system. That's why we say it is lambda subscript s. So lambda subscript is 15 into lambda, while lambda is the failure rate of the individual component. To accomplish the desired reliability of 0.98, that is pre-specified after 3000 of operations. So this is the system reliability, this 0.98, and you apply this formula, that means e to the power minus lambda s into 3000. So you compute the value of lambda s, that is 6.734 into 10 to the power minus 6. Is it okay? So failure rate of each component is obviously lambda s divided by 15, that means 4.48 into 10 to the power minus 7. So you just follow the steps one by one. So you will get all the details, you will understand all sorts of computations and why and how these computations are necessary. So similarly, the mean time to failure for each component will be MTTF is 1 upon lambda. Okay, so these expressions already you are aware of for computing mean time to failure, and the value is this one. Okay, now we will move to the next example. So example 3, determine the number of identical components required in parallel structure. Now we are moving from the series to parallel in order to achieve a system's reliability of 0.999. So that is expected. That means if the reliability is high, what you can assume that the survival time will be more, and at any point in time getting say the function from the product is also very, very high. That means but the value of the product is assured. The individual component reliability is given as 0.85, right? So it is not that high. Determine if the desired level of system reliability is achieved if the same components are arranged as series structure. Is it okay? So supposing the person concerned, he recommends a series structure, but he doesn't know, he or she doesn't know what is the relationship between the system's reliability and the individual component reliability. Is it okay? Now if he or she opts for the series say the structure, whether you can achieve a value of 0.99 for the system's reliability. So here this is relationship, that means the system's reliability expression for the parallel structure is 1 minus this one. Is it okay? That means 0.68. That means to the power n. So it is 0.99. Is it okay? So this is point minus 0.1, right? So 0.32 into 0.01, which gives n equals to 4, right? Series structure, system's reliability 0.68 to the power n. Okay, so this is 0.68 to the power 4, that means 0.2138. Hence the system reliability is not achieved with the series structure. Is it okay? It's very clear. Next problem, that is example 4. Again we refer to the parallel systems, and parallel system is having this many, this is typical parallel systems we have. So for the parallel system shown in figure, determine the system's reliability if the reliability of R1, R2 or R3. This is the general parallel network block diagram. So here what you have, I have shown n number of the components in parallel, but here for the given problem you just assume that n equals to 3. That means just 3 the components you have in parallel configuration, and the corresponding the reliability, component reliability, that means for R1 the reliability is 0.98, R2 is 0.96 and R3 is 0.94. Is it okay? And we are assuming that this component reliability that remains constant, right? That is the first assumption. Find the system reliability for 3000 hours of operation. Find the mean time to failure. If all the components in the systems have an identical time to failure exponential distribution, right? Time to failure distribution is exponential, and we are mentioning identical. That means the failure rate is same with a constant failure rate of 0.0003 per hour. Find the mean time to failure for the system for 5000 hours. What is the mean time to failure for each component should be? Is it okay? So these are the typical problems. So this is your parallel structure. So the reliability of the system is 1 minus 0.8 minus 0.8, 1 minus 0.96, 1 minus 0.94. So these 3 terms you multiply the product term, and then you subtract this value from 1, you get the system's reliability, okay, with 3 components in parallel. The system reliability is much higher than that of the individual component reliability. So this is the advantage. That means if suppose the component reliability you cannot improve beyond a certain value, okay. Now, but you cannot compromise on the system's reliability. So the best option is, can you have a parallel the configuration. So so if you find that today at the present design it is a combination of series and parallel, so can you go for improvement in the design so that the series and series parallel the combination changes to only parallel. So such the effort must be exerted, and this is basically the redesigning effort, okay. So always whenever you opt for a better design we implicitly assume that it will bring in higher reliability of the system. Is it okay? So this is just we are exploring different options, but the present the problem you must be able to quantify. So whenever you carry out such exercises, you will give an idea about how to assess the present system's reliability, or say the component reliability in the existing design. Now the next part is the failure rate for each component is this. 0.0003 per hour, that is the value of lambda, and for 3000 hours of operation, the reliability of the system is this. That means 1 minus, then 1 minus e to the power minus 0.003, that is the lambda, and this is t, that means e to the power minus lambda t, and there are 3 identical components in parallel. So that's why it to the power 3, and ultimately you get the value of 0.791018. Is it okay? So this is the system's reliability. The mean time to failure, that we all know that for the parallel system structure, MTTF is 1 upon lambda into 1 plus half plus 1/3 plus up to 1 upon n, that is the general formula. So here n equals to 3, so you stop it here. So this is 6111.3334 hours. Mean time to failure for each component is 1 upon lambda, that is MDF. Okay, so 1 upon 0.0003, that is this value, that means 3333.3334 hours. Hence, when the 3 identical components are in parallel, the system's mean time to failure has been increased by this one, that is 83.33%. So it is a substantial increase, and for a desired system MTTF of 5000 hours, we calculate the required MTTF of the individual components, and 5000 is 1 upon lambda, like this you apply this formula, and then when lambda is the failure rate of the each component, so you get the value of lambda from here. So lambda value is this one, 0.00036667. Hence the MTTF for each component is 1 upon lambda. So I have written down all the steps. So you need to go through all the steps, and you will get an idea that how many with the different ways the problems can be explained, and you have to answer to the several types of questions raised. Now another examples I am going to discuss, that is example 5. Determine the reliability of the system. The reliabilities of the individual components are given as this: R1, R2, R3, R4, R5, R6, R7 and R8. That means there are 8 components. Determine the failure rate of the system's time to failure. The individual components failure rates, number of units per hour are given as follows. That means this is the individual, for all 8 components the individual values are given. Now how do you get a solution? That means the reliabilities for each subsystems are obtained as follows, right? For the subsystems with components R1, R2, R3, R4, is it okay? The reliability is this one, that is, you compute R1, R2, that means these are in series and then they are in parallel. So 1 minus R3, R4. But by looking at this expression, you will come to know, okay, what is the system structure. So that is one assignment I am giving you. That means suppose this is one configuration, it represents one configuration. By looking at these particular expressions for the reliability, can you draw the system structure? Okay, so when individual values are given, obviously you can calculate the system's reliability with this structure. Similarly, when you opt for this sort of formulation, what is the corresponding system structure? Can you draw it? Is it okay? So that is a part of your problem. So RB, that means the next systems referred to as systems B, and corresponding reliability is RB. So you have R5, R6, R7 components. So they are all in parallel. Is it okay? So there could be different expressions, like say suppose for series you will have one kind of expressions for reliability, systems reliability. If it is parallel, another. If it is series and parallel, so you will have an expressions. By looking at the expressions, can you draw the system structure? Is it okay? So corresponding values are all given for all the 8 components. So the system reliability is given by this one. That means the individual one, that means RA, RB and R8. That means the 8th one, is it okay? 8th one is parallel, it's in a series with RB and series with RA. and within this array you have another structure, within this B, systems B, you have another structure, is it okay, and R8, that means this particular component exists separately, is it okay. So you have this expression, systems reliability. So the failure rates for the subsystems can be computed as follows. That means the failure rate for R1 by R2 subsystem is this one, R1, R2, that is you add them, so you get this one 0.0045. You look at when you draw the structure, you look at the structure, you will get the meaning, and why do you go for adding these two values of lambdas. Similarly, the failure rate for R3 R4 subsystem is lambda R3 plus lambda R4. So you add them. The mean time to failure for the R1, R2, R3, R4 subsystems is this one. Is it okay? So that is this value. The mean time to failure for the subsystems consisting of components R5, R6 and R7 is this one. Is it okay? You just refer to the structure. Already you have drawn that structure, and the system failure rate I will compute, but prior to that, the system's mean time to failure, that is 1 upon this, is it okay, that is 90.5387 hours, and the system's failure rate, that is lambda s, is 1 upon 333.334 plus 1 upon 282.062 plus 0.0045, is it okay. That means this is basically one systems, you have the second systems, and the third one is the component, is it okay. So when you add them, okay, then you get this value, the system's failure rate. Okay, so you can refer to this particular textbook for the details.